Okay, now we're looking at question 3 on the 2026 AP Physics 2 free response section. And here we have an experiment where scientists want to collect data that can be graphed to determine the magnitude of an external uniform magnetic field. Field is directed into figure 1 in the region between the parallel conducting plates that are connected to a power supply of variable EMF epsilon. And the plates are a known distance d apart, where d is much smaller than the dimensions of the plates. So for each trial here, it seems like we're going to have a device that emits charged spheres of speed v through the region, and then epsilon is varied until the spheres move undeflected towards a motion detector. So it seems like they're going to have both an electric force and a magnetic force. The electric force caused by the charged plates of the capacitor, and a magnetic force caused by that external magnetic field. And in order for the charged spheres to actually hit the motion detector and move through the region undeflected, they must have sort of a balanced force situation going on here. So I would imagine that if they are to move through here, we can hypothetically say they're positively charged, which means they're going to have a magnetic force up, and then an electric force down. And those should be balanced with each other in order for them to move through the region undeflected and have a constant velocity. So the scientists have access to a voltmeter, and it sounds like that's all they have. Okay, so just kind of going on this a little bit. So let's read part A and part B together to kind of get a bird's eye view as to how this is going to work. So for part A, we need quantities that could be measured using the available equipment, which sounds like we only have a voltmeter, to determine the magnitude of the external magnetic field. And then we need to describe a method to reduce experimental uncertainty. And then for part B, indicate what we could graph on the horizontal vertical axes to create a linear graph to determine B naught, and then describe the relationship between B naught and the feature of the graph we have in part BI. Okay. So let's start this. So for part A, I'm gonna write this as 1. Actually, before we do that, let's continue that sort of analysis here to kind of get a sense of what the plan is. So we do know that the forces on the particles, so the magnetic force up and the electric force down, if they're positively charged, if they were negatively charged, these would just be opposite directions. So we would still have a balanced force scenario. Those have to essentially balance each other out. So the magnetic force magnitude should equal the electric force magnitude. So we'll have QVB is equal to QE. And so the charge is going to not really matter here. And so the speed is going to depend on the electric field divided by the magnetic field. Now, because this is a capacitor, we'll say the top plate is positively charged because I believe that was connected to the positive terminal of the battery. We're going to have a delta V here, potential difference of magnitude epsilon, since that's the power supply. And that's going to create our uniform electric field in this region. That uniform electric field should be the potential difference divided by the distance between the plates, which is epsilon over d. So we'll actually substitute that here. So that means that the speed should depend on epsilon over d divided by b. And so our final expression is epsilon over bd. And so if we think about sort of rearranging this for part B, it sounds like we can vary the power supply EMF and measure that with a voltmeter, and then record what the corresponding um, distance the plates need to be. Continuing on. So it sounds like we're going to collect data that's going to vary both the speed and the resulting EMF. And so if we think about how this might work, we'll have something like the EMF should equal the magnetic field strength times the distance between the plates, times the speed of the particles. Perfect. Okay, so for part A, we'll say for each trial, actually no. Okay, For part A, we'll say emit the charged particles at speed v, then vary the EMF until the particles move in a straight line and hit the detector. We'll probably need to measure the EMF with the voltmeter. And that should be one of our data points. And then we'll just have to repeat this for different corresponding speed values and EMF values. Different values of speed v and corresponding EMF values epsilon. And that should do it. So by repeating it multiple times, we'll reduce experimental uncertainty. Okay, now for part B, it seems like our relationship is going to be that the EMF is equal to the magnetic field strength times the distance between the plates times each corresponding speed. So we'll probably want to graph speed on the horizontal axis and EMF on the vertical axis. And that will allow the slope of our graph to equal, well, the magnetic field strength times the distance between the plates. So we'll put that down as an option. So graph epsilon versus v from the data sets. Slope of the line is equal to the magnetic field strength times d. So we can say set the slope equal to, so we could say B naught, therefore B naught is equal to the slope divided by d, and that should work. Alternatively, we could have also said we could just make our slope the magnetic field and create a data set that is both the distance times each corresponding speed, and then the EMF on the y-axis, and say graph. I think either of these are correct. And then in this particular case, because we're already incorporating d for each value of speed, the slope of our line should just equal the magnetic field strength. And that should be it for part B. I think either one of those, the red or the blue option, will work for part B. Okay, on to part C. Following information applies to C and D. We have a second experiment. It looks like we're shooting a charged particle into a magnetic field and watching it move in a circular path. And we want to determine the mass m of this charged particle. Each particle has a charge of 6.4 times 10 to the negative 19 coulombs. Each trial, the particle is emitted with speed v 3 times 10 to the 6 meters per second toward a region of external uniform magnetic field. And then the radius r is shown. So it looks like positively charged since they're deflected downwards as they enter the field. And we kind of have to relate this data set to each other. So we could say that because as the particle moves in the field, the magnetic force is acting centripetally and pointing towards the center of the circle. We can say the magnetic force is equal to the centripetal force. So QVB is going to equal m times the quantity e squared over r, which is the centripetal acceleration. So QB is equal to mv over r if we cancel out one of the v values, speed values. And it looks like, just sort of relating this data set together, we're going to have something like the magnetic field is equal to mv over q times the quantity 1 over r. So we'll probably have to linearize this data by taking the inverse of the different radii for each path, for each trial. Perfect. Yeah, so we will make this our y variable on the vertical axis. We will make this quantity our x variable on the horizontal axis. And then our slope should equal mv over q. And since we have given values for the speed and the charge, we can then set the slope of our best fit line equal to that expression and then solve for m. So let's start that process. So we should graph the magnetic field in units of Tesla. So I'll check that really quick. Yep. And then on the horizontal axis, we'll graph the quantity 1 over r, which is going to have units of 1 over meters. Okay. So we will have to create that data set. So we'll do that over here. So the magnetic field isn't going to change at all. So those values will be the same. 0 0.04, 0 0.06, 0 0.14, 0 0.16, and 0 0.20. Now we'll have to create 1 over r. And so for that, we will have to take the inverse of all of these values. So to do that, we'll use a calculator. So the first one is the inverse of 1.8, which is about 0 0.56. The inverse of 1.2, which is 0 0.83. The inverse of 0.5, which is 2. The inverse of 0.4, which is 2.5. And the inverse of 0.3, which is 3.33. Okay, so it seems like one of our R values go from 0 to 4, and our magnetic field values go from about 0 to 0.2. So looking at the scale of this graph, we could probably say these will go from 0 to 4. So we'll just do 0, 1, 2, 3, 4, 5, and 6. And that should capture most of the graph. And then on the vertical axis, we'll go from 0 to maybe 0.25. So we'll go by 0.05s. And that should scale pretty well. And we'll be using most of the region in this, which should be good. Okay, so let's actually start plotting the data. So the first data point is 0.04.56, or rather 0.56.04, which is probably somewhere around here. Second one is 23.06, which is probably somewhere around here. Third one is 2.14. So that's a little further out, easier to plot. Next one is 0.16, 2.5 and 0.16, which is right here. And then the last one is 0.2, 3.3 and 0.2, which is 3.3 and 0.2 is probably right around here. So there we go. Now all we have to do is draw our line, and we'll do that. Use a different color for that. Draw a best fit line through. I think that looks reasonable. Okay, I think that looks pretty reasonable. So now that answers part C. So for part D, we'll have to calculate m from the best fit line. So we'll need to find 2 points on the line and then find the slope from there. So we can maybe take this point here and then a second point of the line. So this point is 0.07. And then this other point we identified is 2.8 and 0.17. Okay, so we'll find the slope of our line. So it should be 0.17 minus 0.07. We'll write it out over 2.8 minus 1.0, which should give us a value of about 0.056. Perfect. So now we know that the slope of our best fit line is 0.56, and that should be equal to mv over q, which is m times the speed of each particle, which I believe was 3 times 10 to the 6, and then the charge was 6.4 times 10 to the negative 19. Okay, so we'll plug those values in. 3.0 times 10 to the 6 meters per second. And then this was 6.4 times 10 to the negative 19 coulombs. By the way, the value of our slope, units of our slope are Tesla, 1 over meters, 1 over meters, Tesla. So this should be Tesla meters. So 0.56, we'll write that out here. 0.56 Tesla meters. So when we solve this out, we should get units of kilograms. So we'll take our slope, multiply by 0.056 times 6.4 times 10 to the negative 19 divided by 3 times 10 to the 6. That gives us a mass of about 1.19 times 10 to the negative 26 kilograms. Perfect. I think that answers question 3.